the first one, I stole some of these out of the book, so if you kind of want to follow along in the book with what we're doing. I want to find all global extrema for the function x squared on the interval from 0 to 2, closed interval. Here it's a good idea to know what the function looks like. So if I were to graph this, it would look something like this. We'd have a point at 0, 0, we'd have a point at 2, 4, and we would have a point at 1, 1. So it looks like that. Do you guys agree with that? So where would we have global extrema? I'm going to call it absolute. So where would we have an absolute minimum?
At 0, 0.
Okay? And convince me that that's the minimum. We'll talk in the next section about how you formally prove that it's a minimum or maximum. But just convince me from the picture or from the function itself that that has to be the absolute minimum at 0, 0. So the derivative is 0 at 0, but to the right of 0, the derivative is positive, which means that the function is going to be increasing to the right of 0, which means that at 0, that's going to be the lowest value. And where is the absolute maximum going to be? Absolute maximum is going to be at 2, 4. For a similar reason, the function is increasing. So it's increasing to the left of that point, which means that all the values around that point are going to be below it. Does that make sense? Or if you just look at the picture, you can see that's the lowest point on the y-axis, and that's the highest point on the y-axis. That's kind of the idea here. All right, so we have the same function. But now we are not on the closed interval, but we have an open interval, at least open to the left. So it's going to be open at 0 and closed at 2. Where are we going to have an absolute minimum here? Nowhere. None. How about absolute maximum? Yep, same thing, 2, 4. This is no different than the other one, right? Good with that? All right, how about this one? What do you think? Minimum at the origin and absolute maximum? None. You guys see why? Cole, question?
What would happen if you used the same function but made the interval -2?
So on this one, it's going to look a little different because we're changing our interval here. So we are on the closed interval from -1, 1 to +1, 1. It's going to look like that. So where are we going to have an absolute minimum?
0,
0,
0.
0. I agree with that. Now, can anybody try to make a stab at a calculus reason for 0, 0 being an absolute minimum? Okay, so the slope of the tangent line is 0. Tilly, what'd you say?
The limit approach is 0 from both the left and right.
The limit of the function? Okay, I agree with that, except even if the function looked like this to the left, the limit would still approach 0, right? But then it wouldn't be a minimum anymore. So the first thing that's important to us here is that the slope of the tangent line is going to be 0 there. And we could figure that out by taking the derivative. We'd get 2x, set that equal to 0, and we get x equals 0. All right, so we know that the slope of the tangent line is going to be 0 there. So I need just a little bit more. Why is that going to be a minimum? Because the slope of the tangent line would be 0 at a maximum also. Cole?
The slope of the tangent line would be 0, and it's also the lowest point of the function.
Okay. Why?
Because the line, like, it goes down, but it never goes lower than the other two.
Decreases to the left and increases to the right.
Okay, yeah, so Cole had the right idea until he's formalizing a little bit more. So to the left of this point, the function's decreasing, which means that the values are greater than the point to the left of it. And to the right of the point, it's increasing, which means the values to the right are also greater. So that means that it's going to be at least a local minimum, and we don't have any other points around it that could be a global minimum, so that's going to be our absolute minimum. All right, and like I said, we'll talk more about how we formalize that and how we write that in a later section. How about an absolute? Let's go with a maximum now. Where is the absolute maximum of this function? Yeah, it actually has two of them. -1, 1, and 1, 1. Those are both absolute maximums, since they both take on the same value. Does that make sense? Okay. How about this one? We could graph this and see what it looks like. And if I were going to do that, I would graph it in a window that only included the values from -2 to 3. In fact, if you go to your window in your calculator and put in -2 and 3 for your x minimum and x maximum, then you can zoom fit and it'll automatically set the y values. What do you think, though? What if I didn't want to go to my calculator and graph it, or what if this wasn't on a calculator section of a test? What could I do? Okay, I could just check points. Can I check just any random point? Should I just try every point between -2 and 3? That might cause some trouble, right? Because there's a lot of them, like infinitely many. What? Okay, I could check all the integers. What if it happens at like 2/3? Then that sucks and we get it wrong. What do you think, Tyler? Yeah. So remember what we said. The only places where we could have a maximum or a minimum value are at the endpoints and at the, what were they called? Starts with a C. Critical points. So we're going to find the critical points by taking the derivative. So the derivative of this function is 2x minus 2. And to find critical points, then we're going to figure out where that's equal to 0 and where that's undefined. Well, it's never undefined, is it? No. So we're going to just set it equal to 0. So we're going to say 2x minus 2 equals 0. And we get x is equal to 1. So we have a critical point, we'll call it a CP, at x equals 1. Now why is that useful? Because that is a possible extrema. We don't know if it's going to be a local or a global minimum, global maximum, absolute minimum, I'm sorry, that's the same thing, local minimum, local maximum, or it might not be anything. It's possible that it's not an extreme value in any way. I know that it's going to be because it's a parabola, and so at that point we're going to get the vertex of the parabola. But what can we do now to check to see if that's a minimum, maximum, and where else might we have minimums and maximums? The endpoints. So what we're going to do is we're going to check the critical points, and we're going to check the endpoints and see what the value of the function is at all of those places. So what is the value of the function at x equals 1? What do we do? Plug it in. 1 minus 2 plus 1 is 0. Okay. We also need to check the endpoint. So what is the value of the function at the left endpoint? Negative 2. We get 4 plus 1 is 9. Okay. And what is the value of the function at the right endpoint at 3? We get 9 minus 6 is 3 plus 1 is 4. So now we can answer the question. We have an absolute minimum where? At 1, 0. Why 1, 0, Jeremy?
That was the bottom of the parabola.
Okay.
The slope was 0.
So it was the bottom of the parabola. We do have a slope of 0 there. So looking at these values that we got here, how do you know that's a global minimum?
The smallest.
Yeah, it's the lowest value of all of the possible extrema. So one of these three is going to be your minimum, one of these three is going to be your maximum, and one of them is not going to be anything. So what is the absolute maximum going to be? Negative 2, 9. So without even looking at the graph, I know where the minimum is and what the minimum value is, and where the maximum is and what the maximum value is. It's kind of cool, isn't it? Okay. You want to do the local examples tomorrow?